You're listening to a podcast from 702 and Cape Talk.
9 minutes after 10. I've only just discovered how efficient voice notes are. So for me, it's a new thing. I think I've made it in life. Mario was just laughing at me. I speak into my WhatsApp to give someone a voice note. Perfect diction, of course. Efficient use of language. And then you realize you didn't record the darn thing. So I'll have to wait until I have the next spot break. It is 9 minutes after 10. This being a Friday, it means it's time for The Naked Scientist.
702 and Cape Talk.
The Naked Scientist.
Call us right now because it gets very busy with your questions for The Naked Scientist on 011 883 0702 in Jersey Land and here in Cape Town on 021 446 0567. And the folks in the cheap seats, you can tweet your questions for Chris at Cape Talk at Radio 702 or at UCBS. Hello, how are you, Chris?
It still makes me laugh every time you say that. All the entire Twitter nation. I mean, how many billion people use Twitter and they're all in their cheap seats? Donald Trump uses Twitter.
Well, there you have it. I mean, how much more do you need to justify my statement? I am fascinated, Chris, by this week's science story we're going to focus on because it is a bloody good one.
Yes, and what scientists are announcing this week, two independent groups of researchers actually, they have made for the first time stem cells, effectively bone marrow stem cells that can make all of the elements in your blood. So new red blood cells, new white blood cells, and therefore your immune system and the mechanism by which blood clots. This is a big breakthrough because while people have got tantalisingly close in the past, they've never quite brought this over the line. And now there's two groups of researchers in America have managed to do it. So Raphael Liss is the lead author on one of these papers in Nature. He's at the Weill Cornell Medical College in New York. The other group is led by a guy called George Daly, and he's at the Dana-Farber Cancer Institute in Boston. They've both taken similar but slightly different approaches to get to the same outcome. What the first group did was they took the linings of blood vessels, these are called endothelial cells, out of blood vessels in mice, and they added to them 4 factors. We call these transcription factors, which are effectively switches inside cells that can turn whole constellations of genes on or off. And they found the right combination of these factors, which will turn on the right sorts of genes to, over a 28-day period, reprogram these blood vessel lining cells from adult mice to become bone marrow stem cells. And when they were then put into an animal that had had its own bone marrow removed, these stem cells could repopulate the bone marrow and then produce all of the elements of blood in these mice, and they could do this for the lifetime of a mouse. And there was no evidence of malignancy. And we worry about malignancy because when you manipulate cells and turn them back into stem cells, there's always a concern. Have you flipped a cancer switch or something that could make these cells have the ability to produce tumours? They didn't see it. The other group did it slightly differently. They actually, as one commentator put it, went via the moon and back to take an aeroplane flight because they first of all turned cells into what we call IPS, or induced pluripotent stem cells, very, very unspecialised cells resembling embryonic stem cells, and then they turn those back into bone marrow stem cells. But they did it with human cells, showing that it's possible in humans too. So we have 2 papers here, both of which have achieved a first, which is to make these stem cells that are in the bone marrow, which can grow all the elements of blood, and bone marrow transplants save thousands of lives around the world every year, but they have to come at the moment from another human donor. And they're in short supply. Finding a good genetic match means there's always problems. If you could make your own bone marrow stem cells to fix your bone marrow with a technique like this, you'd get around a lot of those immune problems, and you wouldn't have the same supply problems that we do at the moment. So a really outstanding piece of work for both of these groups.
Fantastic. Great research there. Let's go to Santon. Mo, good morning and welcome to the show. What is your question for Chris?
Hi, how are you?
Very well, thank you, Mo. Go ahead.
Thank you. The question is, I've just started being interested in space travel, mainly from the movies. And I've discovered there's a spacecraft that's been orbiting Saturn for the past 10 years. I think it's called Cassini. I want to know what sort of fuel is being used to take these spaceships or spacecraft so far away and to keep them going for 10 years or more, even longer. And why can we not use this technology for ourselves? Thank you.
Hello, Mo. Yes, you're quite right. That's the Cassini orbiter. In fact, it's in the last year of its life because in September of this year, the group that put Cassini up there are going to crash land it into Saturn itself, into the gas giant. And the reason they're doing that is that they don't want to contaminate or pollute any of the moons that they've also been studying around Saturn, because there may well be other things from the Earth's surface on those moons, and on the orbiter, and we don't want to deliver whatever that material is onto the moon and contaminate it, so they're going to crash land it. Actually, the interesting thing about Cassini, one of the people who was involved in that mission is a guy called John Zarnecki. And when I was a medical student at Cambridge University, John came and gave a talk to the Science Society, and I was so taken with his talk. This is in 1997, because he said, I've helped to build this thing, and we're going to launch this next year. And he got me to sign a piece of paper, and he said, because technology's moved on when we've been designing this probe, actually we can now pack a lot more stuff into the probe than we could before. So we've got a bit of free space on board. So we're going to send a load of people's signatures to Saturn. And so I signed the piece of paper. So my signature went to Saturn, actually on the Huygens lander that John built, which was the deployed lander that landed on the surface of Titan, Saturn's largest moon. But that's an aside. How did it get there? The reason it took 7 years, between 1997 and 2004, which is when it eventually got to Saturn, is because the spacecraft don't go in a straight line. What we do is make or take advantage of what is called gravitational assist. You get a slingshot. So when people are plotting the trajectories of these probes, what they do is that they plot a contorted course that goes around the solar system a few times, heading towards other planets, and you can use the gravity of other bodies in the solar system to give you a slingshot effect to speed you up. And this means that a journey that would take far, far longer and would involve enormous amounts of fuel can take a lot less time. But it still takes years. So that's one way of doing it. How they power them, apart from rocket fuel, because obviously you've got to get the thing out there and give it a push in the first place, and that's where rocket fuel comes in. You can also do things like solar sailing. Some probes that are being considered, or some designs for spacecraft being considered, have a big sail where it collects light from the sun, and when light hits it, light impacts a push or gives it some momentum, and that can push things along. So that's another way of doing it. Also, they use radiogenic supplies. So the original, the Voyagers and things that have gone out and left the solar system now, they actually have a radioactive source in them, and the radioactive source is breaking down and producing heat, and the heat is then fed into what we call a thermoelectric generator. This is a system that can turn heat into electricity, and this means that way out in deep space, where there's not enough sunlight to run a solar panel, which is the other way of doing it, you can still make electricity. And so a lot of these probes use one, some, or all of these techniques.
Great stuff. 17 minutes after 10. This is The Naked Scientist, and we're taking your questions until 10:30. Fastest fingers first.
702 and Cape Talk.
The Naked Scientist.
20 minutes after 10. Let's go to Auckland Park. Stephen, good morning.
Good morning, sir. I want to ask a question with regards to general relativity and telomeres. Basically, general relativity has got to do with, space-time distortion in relation to gravity. And also, we age because our telomeres get shortened during replication. So I want to ask, by virtue of the fact that astronauts that are in space get a little bit, they age less than human beings down Earth. So I just want to make a connection. Is it possible that our telomeres may get shortened due to gravity as well? I'm not sure. I've been thinking about it, so I just wanted to pose that to make a sense. Thanks.
Okay.
Wow, what a deep thought.
Good luck. Discuss that one for 50 marks.
First of all, what do we mean by telomeres? Well, this is an important point, because every single one of our chromosomes, and you've got 23 pairs of chromosomes in each of your cells, at the ends of those chromosomes are caps, which look a bit like the piece of tape you wrap around the end of a shoelace that keeps it from fraying. And these, as your cells divide, and you age, because every time your cells divide, you're making new cells, they get shorter. And it would appear that the older a set of cells are, the shorter their telomeres are, and when they get to a certain age, the telomeres go, they're completely vanished, and then the cells can no longer divide. And this is referred to as the Hay-Flick limit. Cells have a finite number of cell divisions they can go through. And this is a protective mechanism to stop cells continuously and relentlessly growing in order whereby they may accumulate various dangerous and harmful mutations, changes in their DNA that could lead to cancer. So you try and protect from that by stopping cells dividing, by giving them a finite division lifetime. Now, cancer actually thwarts this mechanism and works out how to replace its telomeres so it's not encumbered in this way, which is why cancer is a problem and cells do grow out of control. But what the questioner is asking is, given that we know that time can pass at different rates for different people, so if you're travelling on an aeroplane, for example, then you're going very, very fast compared to people on the surface of the Earth, and therefore time passes slightly more slowly for you than it does for the people left behind on Earth. That's Einstein's theory of special relativity. There's also another phenomenon that the questioner refers to, which is general relativity, which is it's not just speed, how fast you're travelling, that can distort time. It's also mass. And so if you're very close to a massive object like the Earth, which distorts the fabric of space and time, then time passes at a different rate on Earth and close to that distortion than it does further away. So if you travel out into space as an astronaut, then you're going to experience time at a slightly different rate than someone who's close to the Earth's surface. And you've got to take all these factors into account. And so what he's saying is, will that be reflected in how my telomeres age? And the answer is that it's all relative, no pun intended, because for you, time continues to pass at the rate that time passes. You're not going to measure a demonstrable difference in the rate of time passing, but it's relative to you that everyone else experiences time passing at a different rate. So if you were to compare your telomeres with someone on Earth's telomeres, and you've been travelling at high speed or you've been out to space, yes, there would be an absolutely tiny difference in the size, because the time difference for an average space journey is going to be absolutely tiny. But yes, in theory, the person who has aged a bit less because time has passed more slowly for them than it has for you, they would have telomeres that were slightly longer than yours, assuming your telomeres are identical lengths when you both were both on Earth together before the space mission started.
Carol, good morning.
Morning to you. My question is, has there been any progress in the research for macular degeneration? I am currently having Avastin injections in my right eye, and my friends tell me that although I'm told here that there's been nothing, they read in the British papers that they are working on things. So I just wondered if there was anything. Thank you.
Oh, hello, Carol.
Thank you, Carol.
Well, first of all, what's macular degeneration? This is one of the commonest causes of sight loss as we get older, and as the population of the world ages, because people are living longer lives, more people are moving into the bracket where they've lived long enough for this to become a problem. And when people have this problem, it is damage to the retina, which damages the photoreceptors, which are the rods and cones that convert light waves into brain waves and enable you to see. And unfortunately, as you will be too familiar, it robs people of the sight in the central part of their vision, the bit that you use when you want to look at someone across the room and recognise their face, or pick up a book and read the text, because all you see is a much less acute, or in some cases a blacked out area of your visual field. So the problem is we're losing photoreceptors. Why is that happening? Well, there are two forms of macular degeneration, what we call a wet form, where blood vessels proliferate into the eye and they leach out contents which is toxic to the retina, and there's also a dry form. What researchers need to do to repair people whose eyes are already affected by macular degeneration is to put the photoreceptors back, give them new ones, and there's research being done, and it has got to a certain stage of success in mice where you can do that. You can use stem cells to put new rods and cone precursor cells into the retina. They go to the right place and wire themselves in. It looks like some of these animals are regaining some of their ability to see. There are also ways of stopping the condition advancing in the first place, and that's the other thing that researchers are concentrating on. One of those treatments is one you mentioned. It's called Avastin. This is a drug which can stop the blood vessels proliferating in the back of the eye and leaching out their contents, which are toxic to the retina. So researchers are looking at that. And then there's ways of keeping the back of the eye that nurtures and nourishes the retina in the first place, the retinal pigment epithelium, keeping that healthy so that it can keep the photoreceptors healthy. There's been a lot of developments, actually, in the last 5 or 6 years towards achieving these goals, and even making bionic implants which can go in the back of the eye and replace the photoreceptors with electronics. People are even doing that, and they're also getting some degree of success, although it's very early days and we're nowhere near restoring the kind of vision that your own natural system has in it to people. But certainly things are on the move, and we can hold this condition back and slow it down, and you can also, in some cases, restore some elements of vision for people. So it's a very exciting time, but we're not there yet.
Great progress, though. Let's go to Four Ways next, Chris. We've got on the line with us Makoseni. Makoseni, thank you for holding on. You've been holding on for a while. What is your question for the Naked Scientist?
Thanks, Tobias. Chris, I want to know about the real origin of what I can call complex life form. I understand that in the beginning there were single-celled organisms all over the world or all over the planet, wherever it might have been. And how did these single-celled organisms then mutate to form the heart, the lungs, the eyes, to accelerate the current life form as we know it, human beings and other animals?
Yeah, lovely question, but a very complicated one, which
Thanks,
is actually
Makoseni.
encapsulating, something like 4 billion years of evolution. Wind the clock back about 3.9 to 4 billion years. That's when we think the first life was detected on Earth. And the evidence for that comes from various places, but including Australia. Western Australia has some of the oldest rocks on Earth, and trapped into those rocks, people have found tiny particles, including there was a paper in, I think it was Science last year, by a group led by a guy called Nimmo in America. And they discovered in these rock particles there were trapped inclusions of carbon, and when they looked at the isotope profile of the carbon, they found that it was compatible with life. So we think life probably got going on the early Earth very early, but that life was very simple, and it was microbial, single-celled organisms, microbes like bacteria. And we don't see any evidence in the fossil record then of anything really changing for about 3.5 billion years. And it's only about 500 million years ago, 600 million years ago, that suddenly we begin to see what could be construed as more complicated multicellular or metazoal life. And one of the examples of that, there's a nice fossil that was described a couple of years ago by a lady in Cambridge. She actually was doing the work in Canada, and it was of a fossil called Fractofusus, which lived on the seafloor, and it seems to have been reproducing by putting out these runners, a bit like a strawberry plant, and occasionally also breaking a bit of itself off and sending it down on the tide. So there's a massive gap in our knowledge of how these things went from the single cells that dominated the Earth for 3.5 billion years to then suddenly teaming up and forming multicellular life. What we do think, though, is that if we look at our cells, a modern human cell, it's got a nucleus in it, which is where all the DNA, the genetic information is. It also has these other structures called mitochondria, which are where the energy comes from in the cell. And the mitochondria are the same size and have DNA in them, very similar to bacteria. So scientists think that at some point in history, and this was a lady called Lynn Margulis who put this forward as the endosymbiont theory, we think that cells learned to team up and they incorporated into themselves the knowledge of bacteria and gave bacteria a home, and the bacteria they gave a home gave the cells back energy. That was the trade-off, and that led to cells then working as units, and then the cells then learned, in inverted commas, to team up and form bigger functional units, which eventually then evolve into whole organisms. But it's extremely hard because the fossil record captures hard, bony things. It doesn't capture biochemistry very well, so we have to sort of infer and deduce a lot of this stuff and speculate. So it's very much a black hole.
Chris, love the insights. Thank you so much. We'll do it again next week.
Thank you, Eusebius. Thank you, everyone.
And
See you
have a
soon.
fantastic weekend and week ahead.